Hello everybody, and welcome to lecture number 3 in this series on cosmic vision. Following on from my previous lecture, which was based around the idea of attentive eyes on the night sky, we're going to be turning our attention today on witnessing fireworks. Now, in this country, 2 weeks ago, lots of fireworks were set off in the night sky. The 5th of November in this country is very often associated with bright and noisy fireworks that scare the basset hounds and the spaniels of this country. This practice, this tradition, is commemorating something that happened over 4 centuries ago. Although the historical detail is a little sketchy, we do know that thanks to the endeavours of Guy Fawkes and his co-workers, an attempt to blow up Parliament was in fact thwarted. Fireworks, and this keeping this tradition alive, remind us year by year of this event 4 centuries ago. For the benefit of those who did not grow up in this country, you may be interested to know that as a kid at school, you are made to chant this rhyme. Remember, remember, the 5th of November. We see no reason why gunpowder treason should ever be forgot. You're made to chant this poem in return for being able to watch the exciting fireworks at night. So despite the sketchy historical detail, the memory of that thwarted event 4 centuries ago, Parliament was not blown up, the gunpowder never did the damage it was intended to do. Nonetheless, it is etched in the memory of most school children who grow up here. So that was back in 1605, but 1 year prior to that, there was another major firework that really did happen this time. It wasn't thwarted, and it happened in the night sky. This event in 1604 was a supernova that I've mentioned previously in this series of lectures that we now know as Kepler's supernova. It was in October of 1604. It was when Gresham was still on its first professor of astronomy. This particular supernova explosion in the night sky was brighter than the planet Jupiter. At its peak, it was brighter than any other star in the night sky. It had an apparent magnitude of minus 2.5. That's very bright indeed. And so that means it was actually visible to the naked eye easily, and it was thus for more than a year. What happens in a supernova explosion? Well, a supernova explosion ejects quite a lot of mass, more mass than several of our suns. And it does so at speeds of thousands of kilometers per second. The energetics involved are just vast. The kinetic energy of the gas that gets ejected out in that explosion is something like 10 to the power of 44 joules. That's a 1 with 44 zeros after it. It's such a large number, we don't use words like billion or trillion. It is way larger than that. It is also way larger, just to try and give you some calibration of this, it is way larger than the energy usage of any one country on this planet, or even all the countries put together. The typical energy usage in the UK in recent years is something like 10 to the power of 19 joules. So that's obviously a 1 and 19 zeros. A vast amount of energy, but utterly dwarf in comparison to the kinetic energy of one of the most spectacular fireworks we can see in the night sky, a supernova. Well, this is what the supernova, Kepler's supernova, looks like these days if you observe it in the X-rays, as was done fairly recently by the NASA and ESA X-ray satellite known as Chandra. And lots of beautiful investigations have been done on the nature and the energetics of this plasma to elucidate the nature of its explosion and what was the progenitor, the precursor, the trigger for this spectacular firework in the night sky. A supernova is really a spectacular firework. They happen not when a star is born, but when a star dies. A supernova explosion is, as I said a few lectures ago, responsible for putting what astronomers call heavy elements into the interstellar medium, from which other stars can then form, and from which other organisms, such as life itself, can form. I am made of carbon and oxygen and nitrogen and a whole bunch of other trace elements. It would not be so if we did not have explosions in the night sky from supernovae and from novae. Something that's particularly exciting about supernova explosions is that they can give rise to black holes. And as I mentioned in the third lecture of my series of Gresham lectures last year, black holes are terrifically exciting. They are the origin of some extreme phenomena in our galaxy and all across the observable universe. That I discuss in some detail in the lecture that I gave almost exactly a year ago. So how often do supernova explosions happen in our galaxy? Well, as we look back at historical records, and they are of course varying in their descriptive degree of precision and detail, but very roughly it looks like the rate at which we get a supernova in our galaxy is on average something like once per century. This is not very frequent, and it is not as frequent as some of us who would like to study the processes of supernova explosions would like. But it is nonetheless stochastic, meaning it's unexpected. It is not obvious when these get triggered. And we have not had a supernova explosion in our galaxy since the one the year before Guy Fawkes and his co-workers were on the point of blowing up the Houses of Parliament here in London. 1604 is a long time ago, and if we want more detail on galactic supernova explosions, we have to go further back in time and look at other historical records. As I mentioned in my lecture in May, the Chinese were exemplary in their record keeping of stochastic phenomena such as supernovae. Well, they didn't use the language that we use now, of course, but they do use language like guest star, a star that appears, a star that is not part of the firmament that gradually rotates from east to west, from sunset to sunrise through the night. So, by the way, I don't speak Chinese, but I'm told that what is highlighted here represents the historical record of a fantastic supernova explosion that went off in 1054, the remnant of which contains lots and lots of debris of the supernova explosion, and that we now know as the Crab Nebula. I talked about this a little bit in my previous lecture at the end of last month. The Crab Nebula, also known as Messier No. 1 in the catalogue put together by the Parisian astronomer Charles Messier, is beautiful and rich in structure, which is simply laying out for us the debris of that explosion that took place in 1054. I would really love it if there were a galactic supernova in my lifetime, but there could well not be. We haven't had one since 1604. But more recently, there was a supernova that you could see pretty much with the naked eye at night from Earth, or at least if you were in the southern hemisphere, you could. 3 decades ago, there was a supernova in a very nearby galaxy. Let me first tell you about that nearby galaxy. So I'm showing you here in this beautiful image, which from bottom left to top right shows the plane of our Milky Way galaxy. This image was taken by my colleague Steve Lee. And in addition to showing the galactic plane very, very clearly, you can also see what may look from this particular picture like two blobs of fuzz, and indeed at some level to the naked eye that's how they appear, but they are in fact nearby galaxies. Now obviously it's only been possible to confirm their nature as distinct galaxies, entirely separate from our own Milky Way. Previously, in years gone by, when, for example, the Aboriginals of Australia, who very attentively watched the night sky in that very non-light polluted part of the world, could see bits of fuzz which clearly were different from the normal stars. I think back in those times, there was the supposition that they were just bits of our own galaxy. And indeed, if you don't have the benefit of telescopic assistance, as we have today, bits of fuzz in the night sky would be very, very hard to determine the nature of. This particular image that I'm showing you here has two things which to the unaided eye would look like bits of fuzz. But in fact, the one on the top right, NGC 288, NGC standing for the New General Catalogue of Interesting Things in the Night Sky, that's just a cluster of stars in our own galaxy. A star cluster is a big ball, a big collection of stars that are orbiting around one another, bound together by self-gravity, in other words, by the gravity of one another. You can think of it as a micro-galaxy or a nano-galaxy within our own Milky Way galaxy. But it's definitely within the confines of the Milky Way. On the other hand, what I'm showing in the bottom left, NGC 253, that's a galaxy all on its own. And with the help of fairly straightforward telescope investigations, it's very easy to show that's a galaxy entirely outside of our own. And so we term it extragalactic. It is an external galaxy. But none of this would have been knowable to the ancient observers of the night sky a millennia or two or more ago. So back to our own night sky, or at least that viewed from the southern hemisphere. That's the plane of our own galaxy, and we now know these two other balls of fuzz are distinct galaxies outside of our own. The dynamics of these galaxies is not unaffected by the gravitational pull of our own Milky Way galaxy, far from it. But they are satellites outside our own galaxy. And if it's a little bit hard to envisage from this almost close-up, two-dimensional representation of the night sky, let me show you an image of a galaxy that's much like the Milky Way, still in our own local group, known as Andromeda. Andromeda is also known as Messier 31, M31, number 31 in that catalogue of Charles Messier. So we believe that this beautiful spiral galaxy is almost a twin of, or at least a sibling, of our own Milky Way galaxy. What you can see quite close to it is a satellite down here on the lower left and on the lower right and towards the middle left. This is Messier 32 in Charles Messier's catalogue, and this is Messier 110. Don't ask me about the order. I don't know why that is what it is. So Andromeda, the twin of the Milky Way, has satellites much like the Milky Way does. In fact, we believe Andromeda has something like 13 satellite galaxies, of which these are the two most prominent. The term satellite galaxy was a term introduced by Edwin Hubble in 1936. So satellite galaxies are a thing. They are little galaxies that move and interact with the main galaxy that they are nearby to. What I'm now going to do is to zoom into the satellite galaxies of the Milky Way, starting with the one that was labelled as SMC a few slides ago, which stands for Small Magellanic Cloud. It's called a cloud because originally it looked cloudy, it looked fuzzy. It wasn't knowable prior to observations with telescopes around the year that it was a separate, distinct galaxy. This is something like 4 degrees in diameter from end to end. It's believed that in times past, it was possibly a barred spiral galaxy that's been rather mushed up and ripped apart from that original beautiful structure because of interactions with the Milky Way, tidal interactions, because of the gravitational attraction between both of them. But interactions between galaxies are another story for another day. Now let me zoom in on one of the other satellite galaxies of the Milky Way. This one was labelled LMC, standing for Large Magellanic Cloud. It's significantly larger, not quite, but almost a factor of 2 larger in mass compared with the small Magellanic Clouds. We believe that the total mass of this irregular galaxy, a neighbour of our own Milky Way, has a total mass that is something like 10 billion times the mass of our Sun. Now, if that sounds a lot, let me just put the LMC in its place. Its mass is probably only 1% of the Milky Way. This one is 10 degrees from end to end. And if you are in the southern hemisphere on a clear night, you really can see it quite resolved, albeit looking quite fuzzy and cloudy across the night sky there. Not wanting to alarm you or anything, but it is predicted that our own Milky Way galaxy and the Large Magellanic Clouds will, in the fullness of time, collide. By the fullness of time here, I'm talking about probably in something like 2.5 billion years. So it's a while yet. Let's zoom in on some of these beautiful structures that we see laid out before us in this beautiful image of the Large Magellanic Clouds. And I'm going to zoom in on this central right region where it's rather saturated, there's rather a lot of pink. This particular feature here, this structure, is known as the Tarantula Nebula. Of course, in Australia they have lots of big spiders with big arms, so it's not perhaps too difficult to imagine why this was named the tarantula spider. I'm going to zoom in even further now, and you can see, although it's still a bit saturated, it's a structure that has brightness on lots of different levels. What this particular image is showing is what this bit of the sky looked like before a supernova went off about just over 30 years ago, 33 years ago. So this is a before image, and it's pretty easy to see in the lower left corner what it looks like when this particular star exploded in this satellite galaxy, this external galaxy with respect to the Milky Way. Now, this caused great excitement because it was nearby. You could see this object very, very readily. And let me remark how utterly unusual it is to be able to see the light from one single star in another galaxy outside of our own. The kind of size scales that we're talking about here, the Tarantula Nebula is something like 1/2 a degree across by 2/3 of a degree across. so readily observable, even by a very, very basic telescope or by binoculars. A lot of the early studies and investigations when this supernova had gone off were carried out by the Anglo-Australian telescope, and in particular by my colleague whom I mentioned, Steve Lee. There was a huge amount of excitement, and of course the first thing you want to do when a supernova goes off is to alert the rest of the world and all their telescopes to where to look in the sky. Now, this image here is degree scales, and that's insufficient for the acquisition of a modern telescope. A lot of the acquisition calculations and the early astrometric calculations were done by Steve Lee. This is one of the very early, what we call finding charts, something that helps you find where you want to look at a particular target in the night sky. And although the calculations are rather more sophisticated than this particular photograph of this finding chart might suggest, nonetheless, even to this day, this finding chart is still stuck to the fridge of the control room of the Anglo-Australian telescope as a marker for the excitement of that day and all the science, all the astrophysics that unfolded from being able to watch a supernova explode real time before our eyes, albeit in an external galaxy. This next image was taken by Angel Lopel Sanchez together with Steve Lee, and the star in the very center of that image, the one that's shown here as pink, indicated by the pink arrow, is indeed what that supernova looks like today, 3 decades on from the original explosion. This image is actually taken with the Anglo-Australian telescope, which is 4 meters in diameter. That's practically the size of this hall that I am speaking to you from. And it reveals something of the structure of the gases and the plasmas in this particular bit of this particular satellite galaxy in this part of the southern sky. I decided it would be awfully good fun to see if the Global Jetwatch telescopes, which are a mere 0.5 meter in diameter, so their diameter is 1/8 of the Anglo-Australian telescope, could see anything. And I made it hard for myself by trying to do that via spectroscopic observations, which split up the light into colour or wavelength, which is super interesting to do for lots of reasons, but in splitting up the light, it makes it fainter still. Even with a 0.5 meter diameter telescope, you can make a spectrum of a 3-decade-old supernova and reveal within it iron, helium, nitrogen, hydrogen, oxygen, and all sorts of good stuff, which is a reminder of what I said earlier, that what are called the heavy elements by astronomers are splat out and radiating even today from a supernova explosion. Well, I am not alone in looking forward to the next galactic supernova. My Global Jetwatch observatories are eager and ready to go. But a spoiler here, we could be waiting a very long time. As I mentioned, supernova explosions, these most energetic fireworks in our night sky, are stochastic. They are unexpected. Saying that there is an average of once per century is not a predictive statement. We are not owed 1 supernova per century. So let me take you back to the image of the night sky in the southern hemisphere with the galactic plane going across. And I've highlighted here some stars that are unfamiliar to those of us who reside in the northern hemisphere. This bright star here on the right is called Canopus. The bright star noted in orange is the Alpha Centauri star system, which is a triple system containing the star which is nearest to the solar system, known as Proxima Centauri. The coal sack is a region where, let me just zoom in a bit, you'll see it as rather dark near the middle of this image, and I've just zoomed in on it near there. is where there's a lot of attenuation of starlight coming from the central galactic plane. And in this image, it's just below a structure of stars that are very well known if you live in the southern hemisphere, called the Southern Cross. But I want to talk next about this particular region of the night sky known as the Carinae Nebula. This is it back again in the wide field view, and you can see that it's got a brightness and an angular size scale which is a bit reminiscent of the two satellite galaxies that I referred to earlier. So what is it and what does it look like when we zoom in yet closer? So I'm showing here an image, again taken from one of the Global Jet Watch observatories with some of our auxiliary telescopes. This image is something like 5 degrees from one end to another by about 3.5 degrees, something like that. So this structure seen on the left is a zoom in of that pink structure seen across the galactic plane in those preceding slides. This particular image, as I say, was taken with some of the auxiliary telescopes at the Global Jet Watch observatories that have these wide field views to make sure that we can obtain contemporaneous photometric data in support of our spectroscopic data streams. And here they are being admired by some schoolgirls at the India School Observatory that's part of the Global Jet Watch network of telescopes. Here again is that structure, and I can gaze at this image time after time. It has many, many beautiful structures within it. You can see I've put rings around yet more star clusters, which, as I said earlier in my lecture, are self-gravitating groups of microgalaxies or nanogalaxies or picogalaxies within our own galaxy that are orbiting under the self-gravity of the other stars within that little cluster, and a region of hydrogen plasma here in the top right. I can't stop gazing at this image because there's so much rich structure within it. And earlier this week, I asked my graduate student who is working on Carinae to tell me the number of stars in this particular image. Now, of course, I didn't expect him to count them, and he didn't just count them, but he did do a computer analysis of the image to extract every single star in this image. This is approximately a 6 megapixel image, and the computer analysis, after fitting for every single point-like, star-like feature in this image, he reckoned they were getting on for 32,000 stars. Just in this one image, just in this 5 degree by 3.5 degree subset of the plane of our galaxy. You're going to see truckloads more stars in the plane of the galaxy than you are at high galactic latitudes, but nonetheless, I was distinctly surprised by the number 32,000. And of course, there are very many more stars if you integrate for longer and go yet deeper into that particular direction in space. But let's zoom in even further now to see what we see. I wonder if in the centre of the Carinae Nebula, over there on the left, you can make out a tick shape. Zooming in still further there, you can see, or at least part of the tick. A lot of where it's dark is because there's a lot of basically soot or dust, which attenuates a lot of the light coming from there. This illuminated part of the nebula is a lot of it is hydrogen gas. It is illuminated and radiant because of the bright, newly forming stars within this particular region. But I want to zoom in on that very bright star towards the top of the screen. So zooming in just a little bit further. This bright star here, where you can see the spikes coming from it, which are simply an artifact of the nature, the characteristics of the telescope used for this particular imaging. That was the Global Jet Watch telescope at our host school in Chile. This particular star is known as Eta Carinae. Carinae is the name of this particular constellation. In times past, it was known as Eta Argus. Argos was a much bigger constellation that subsumed Carinae and a few other constellations that we now regard as separate. But Eta Carinae is the modern-day name for this very bright star. Eta Argus was the name in the past. Now, this is the most luminous and massive star system within the neighbourhood of our solar system. By the neighbourhood here, I mean within 10,000 light years, something like that. It's been well known for a very, very long time for those of us, or for those of the human race who live at latitudes south enough to be able to see this. A lot of historical data has been collected on this particular system. And in the 19th century, this became the second brightest star in the night sky after Sirius, which is an incredibly bright star. And so throughout the 19th century, people by eye did their best to track how the brightness of the object changed through the years. This is a notebook from one of the people who kept exquisitely detailed records and who kept track of the photometric variation, the intensity variation of the star Eta Carinae with time. And again, it was the method that I described in my last lecture, entitled Attentive Eyes, on differential photometry. Is this star brighter than this one? Is it a lot brighter than this one? So even, as I explained in my last lecture, within the limitations of the non-linearity of human eyesight, it was possible to calibrate the data that was collected by people in times gone by. These data were collected in South Africa, and these little vertical dashes are all about saying, was it 2 lots brighter than this star, or 3 lots brighter than that star? Historically useful data for us. And if you put together all those by eye measurements throughout time, and I'm plotting here on this graph, or I'm not plotting it, this was done by Smith and Frew about a decade ago, but the bottom axis here, all these different numbers are 1 century apart. And that tells you of this great big spike in brightness that took place in sort of 1840 really to 1870. Now, there are a number of theories as to why that great eruption in brightness happened. It's thought by some people that this was because certain stars within Eta Carinae themselves actually merged, causing their own fireworks. Other people think that since it's now known to be a binary star system, maybe it was as a result of the close flypast of the 2 stars that gave rise to this enhanced eruption that happened in the middle of the 19th century. Theories abound, and we can't be super certain of what happened, but it's fair to say that even our investigations today benefit from and feed back to the analyses of ongoing evolution of the Eta Carinae star in the night sky. It's widely agreed that this great eruption in the brightness of the Eta Carinae star was responsible for this amazing bipolar system, bipolar meaning oppositely directed, nebula, which itself was imaged by the Hubble Space Telescope a few years ago. Now, in space, it is very, very common to see bipolar outflows of oppositely directed matter squirted in opposite directions as a result of explosions. And on very many occasions, that's associated with expansion in an equatorial plane, sort of perpendicular to the plane that the bipolar outflow is flowing along. And this feeds into our understanding of what today is that very bright star in the centre of Eta Carinae. My student, David Grant, the one who calculated all of those, the number of stars in that Carinae image that I showed you a few moments ago, he and I have been looking in great detail at the spectroscopy of Eta Carinae's ongoing changing behaviour with time. And this is a movie that David has made of Eta Carinae. We now know it to be a binary star system. This has been confirmed or was originally made secure in 1997 by Augusto Daminelli. And now we know it's a binary star system. We can look with confidence at how those two stars might interact with time. And this is one such simulation that David has coded up, representing the powerful winds from each of the two stars that are orbiting one another in the single stellar entity that we know as Eta Carinae. Analysing this in great detail is huge fun, but the powerful winds that I just showed you in David's simulation on my previous slide do make it very challenging. We get lots of contradictory signals from what the different emission lines in our time-lapse spectroscopy from the Global Jet Watch observatories is showing us. But some recent detailed modelling precisely accounting for the rapid speeds and the opacity, the non-transparency of those two winds, which you saw interacting in the simulation on my previous slide, now enable us to say with certainty that the eccentricity of this binary star system now exceeds 0.9. Well, why is 0.9 a number that you should be impressed by? My fifth lecture in my Gresham lectures in the past academic year, entitled Shapes of Freefall, discussed orbits of objects that were bound together under gravity and under the law of conservation of angular momentum. And in that lecture, I described how the shapes of orbits can be circles, the most familiar thing when we're whizzing a conker around on a piece of string. They can be ellipses, they can be parabolas, they can be hyperbolae, depending on the initial energy and the initial angular momentum of the two stars, or the comet and the star, that form that binary system. Circular orbits are known as having an eccentricity of 0, and unbounded orbits are known as having, or one type of them, the limiting case, are known as having an eccentricity of 1. An eccentricity of 0.9 is the most, getting on for the most extreme bit of parameter space. Let me show you just how extreme it is to have two stars orbiting one another with an eccentricity of 0.9, as we believe to be the case for the Eta Carinae star system. So what you can see here is that an eccentricity of 0.9 means that the two stars, the more massive one we call the primary, the less massive one we call the secondary, as they orbit one another, they spend the greatest fraction of time apart from one another. But they don't fly apart completely into outer space because they are bound together by a beautiful, inescapable combination of gravity and angular momentum. Once per orbital period, however, these two stars come together very close, as happens there. And very close means the potential for fireworks. Now, how often does this happen for Eta Carinae? The orbital period of Eta Carinae was determined, as I said, in 1997 to be something like 2,023 days. That's also known as 5.5 years. How often does this closest approach happen? This closest approach is an event known as periastron, when the stars are near. The opposite, as now, is known as apastron, when the stars are far apart. But periastron in Eta Carinae occurs once every 5.5 years. This event, periastron, occurred in January, February, March of this year, 2020. And despite lockdown, we were able to keep on sky even after that event, as well as during and before. So we've been able to collect data on the exciting processes when they boing together as there. It is entirely plausible that those interactions one day in the course of one of these very close flypasts of periastron now could trigger a supernova explosion in Eta Carinae. So Eta Carinae is certainly a candidate for being the next supernova within our galaxy. So too is Betelgeuse, which I mentioned quite a bit in the last lecture, showing you those images of Rob Tilsley that showed Betelgeuse's brightness, Betelgeuse being the top left shoulder star in the Orion constellation. Those images showed you, thanks to Rob's time-lapse images, how Betelgeuse was changing in brightness. And that's on the list of potential supernova progenitors, stars that one day could go supernova. When I say could go, it is widely believed that it will happen. What's uncertain is when it will happen. We think it's very likely that this will happen for sure in the next 1,000,000 years or so. It will be, whether it's Eta Carinae first, whether it's Betelgeuse first, or another one of the stars that's on our list of supernova progenitors, it is certain it will be very spectacular. It is certain that if a star within our galaxy goes supernova, it will be visible during the daytime, even against the backdrop of sunlight, if it's a star like one of these. It will for sure be very spectacular. They won't wipe out life on Earth, probably. I hope. But let's now look back further in time and think about some other fireworks that we see in the night sky. I've mentioned in a previous lecture about Halley's Comet. And Halley's Comet is one of those comets that completely has a periodic closed orbit around our sun, and so it's seen repeatedly every approximately 76 years. It's on a closed orbit, an elliptical orbit, and so thanks to the work of Edmund Halley, the Oxford astronomer, and a good many other more recent observers, we now know that it was exactly a lot of the orbital elements of the way that Halley's Comet moves around Earth. I'm always delighted that the representation of Halley's Comet itself was even represented in the Bayer tapestry or Bayer embroidery, which commemorated the Battle of Hastings in 1066. I was privileged to be able to look at this beautiful embroidery some years ago when I visited Normandy, and it's an amazing work of art. It is 70 metres long, it is 0.5 metre in diameter tall, and it's telling the story of particularly significant events that were part of the invasion and the battle. And what they're depicting up here is Halley's Comet itself. The timing is known and totally agrees with the calculations and the parameters we now know for Halley's Comet's orbit. This in Latin here, or I'm told it's medieval Latin, there's quite a lot of commentary throughout the 70 metres of the Bayer tapestry, which is in very terse medieval Latin. I am not fluent in Latin, medieval or otherwise, and certainly not the terse kind, but I have some glimmer of the fact that what these three words at the top say is they admire the star. Even though Halley's Comet was a very special kind of star, and not just a point-like object, but an extended fuzzy object, many times when Halley's Comet is seen, it's accompanied by quite a lot of plumage known as a tail, to do with the interaction of the solar wind from our sun and the actual composition of the star itself. It's invariably extended, and due to the perhaps slightly childlike representation of that tail, it does seem likely that whoever it was in the family or the entourage of Norman the Conqueror who pioneered this beautiful embroidery nonetheless called it a star. They admired the star, and I'm sure it was a spectacular sight in 1066 because, of course, light pollution hadn't been invented in 1066. Interpreting comets in the past can be tricky because comets were believed to signify certain events and to have strong meanings. And sometimes it can be a bit hard to decouple the interpretation of comets from the distilled observations, which we might be able to understand more readily in the context of modern understanding of dynamics within our galaxy. In particular, comets in history have a reputation for being portengers of doom, or occasionally of great things. But I think the very fact that Halley's Comet appeared in the Battle of Hastings immediately demonstrates that comets can have very different but perfectly valid meanings for different people. The comet was a very happy sign for William the Conqueror, Duke of Normandy, but for King Harold, for whom things did not end well, as represented in other parts of the Bayeux Tapestry, not so much. The comet was most definitely not a happy sign. Well, other representations of comets in history have led to a certain amount of puzzlement in the past. And in particular, the puzzlement was often connected with all of this kind of striated plumage that you can see in this representation of the 1744 comet that I referred to in a few lectures ago. Many representations of comets, either paintings or wooden carvings, would show this fan of comet tails, these stripes of comets, and that was a puzzle for astronomers for many years. But in fact, this too got resolved when there was a very special and very unusual comet that suddenly became visible, even to the naked eye, in Australia in 2013. This was Comet McNaught, or I should correctly say one of the Comet McNaughts. I'm told that suddenly these beautiful striations appeared as the angle between the comet itself and the sun and Earth's orbit became just right to see the illumination from these stripes, from these striations in the tail. After this critical alignment of the comet and the star, the sun and the Earth came into alignment, it was then possible to think, okay, that's what the previous works of art, the wood carving, the oil paintings were all about. Well, towards the end of my talk now, and bearing in mind the season that we are approaching, let's now travel 2,000 years back in time and 2,000 miles east. The Magi were known to be probably from Babylon or Persia. It's not precisely clear, but they were the astronomers, or perhaps we might more correctly call them astrologers of the day, by which I mean, of course, the night. The Magi were people who looked at the night sky, made observations, and imposed meaning on what they saw. Again, they had the vantage point of a much less light-polluted sky than we have today. and they would be very familiar with the sidereal motion of the rising and the setting of the stars, which we now understand today to be entirely arising from the spin of the Earth with respect to the illumination of the sun. It seems fairly clear from the historical literature at the time that some magi got on camelback and travelled towards King Herod saying, "We've seen celestial fireworks, celestial phenomena." I paraphrase a bit, but you get the idea. They travelled to meet with King Herod, saying they'd seen a star in the east, saying that it moved before them. There are some details of this in Matthew's Gospel, which I think are moderately convincing that the star had non-sidereal motion, pointing to the possibility of it being an object such as a comet or something of that nature, or perhaps the motion of planets. Planets move non-sidereally, i.e. different to the stars. And their interpretation, the interpretation of the Magi, was that it was symbolic of the birth of a newborn king or Messiah. So up they rocked on camelback to King Herod, who was known to be a proud and capricious and slightly insecure ruler, and said, "We've seen these things in the night sky. We think it symbolises the night sky. We've got presents, we've got gifts. Where is this newborn king?" Well, as you may know, King Herod threw a bit of a tantrum at this point, and the Magi made a discreet exit. They and their camels, they travelled down to where they thought the star was standing over, according to Matthew's Gospel, asked around a bit, one presumes, and found their way to a stable where they gave their gifts to a little baby boy. What might that be? What might that star in the night sky have been to cause the Magi to leave Babylon or Persia or wherever they normally resided, hop on camelback, meet King Herod, and then make a discreet exit and see if they could find anyone who had any understanding of someone who might fit the bill as a newborn king? Well, one model that's been suggested is that in 7 BC, there was a succession of 3 conjunctions, great conjunctions, of Jupiter and Saturn. Now, I described in my last lecture a great conjunction as being Jupiter and Saturn come together. And I mentioned then that just 1 month from now, on the 21st of December 2020, Jupiter on the left and Saturn on the right are having a great conjunction. They are coming together. They will be a mere 1/10 of 1 degree apart from one another. 1/10 of 1 degree is about 1/5 of the diameter of the moon. And a good many people, not everyone, it depends on how good your eyesight is, will nonetheless be able to resolve this as 2 objects, Jupiter and Saturn, having come together. And I encouraged you, and I continue to encourage you, to watch Jupiter and Saturn in the next month, just after sunset, and to watch how the separation changes. It'll be closest approach on the 21st of December, and then they will part ways again. Well, this happened 3 times in 7 BC. On each occasion, it was nothing like as close as it will be 1 month from now. What will happen in 1 month from now is really very, very special. So please watch it. Please get used to watching it in the coming month before the 21st of December. But back in 7 BC, there were 3 such great conjugations. The closest approach for each of those 3 was about 1 diameter, so 10 times what we will see next month. Now, I said many people will probably have sufficiently good eyesight that they can resolve, that is to say, separate Jupiter and Saturn from one another, because it is about 1/5 of the moon's diameter. But a great many people at the time the majority of people would easily be able to resolve something that's 1 degree apart on the sky, assuming they had pretty good eyesight. So I don't think it's necessarily compelling that this triple conjunction, by which I mean 3 successive great conjunctions of Jupiter and Saturn, is the Star of Bethlehem, because many people would see it as 2, not as 1. And there's no evidence to suggest that it should be described as plural. But nonetheless, something going on in 7 BC with beautiful bright planets that anyone who looked at the sky would be keenly interested in because they were nice and bright and they moved in a way that was different to the stars, I feel sure that this event, this succession of 3 great conjunctions in 7 BC would be encouraging people to look up. So it's unlikely that this was the Star of Bethlehem itself. What else might it be? Well, Colin Humphreys, who is a professor of metallurgy and materials science, previously at UCL, but prior to that Cambridge, although he's a professor of metallurgy and materials science, he has a number of hobbies, and one of those hobbies is chronology. And he has tried to identify what might be plausible identifications for what was the Star of Bethlehem to fit those scant bits of evidence that we do have from Matthew's Gospel and elsewhere, to see if there is perhaps a plausible identification for what might be the Star of Bethlehem seen by those magi, those guys who watched the night sky. And there are 3 comets that he found in Chinese records that are in approximately the right time. I don't think anyone thinks that Christ's birth happened at the transition between BC and AC, before the Common Era and afterwards. Around that time, sure, but I think the error bar is something like plus or minus a decade. But it's thought that 12 BC, which incidentally is Halley's comet, this was the Chinese record of which corresponds to Halley's comet, that's perhaps a bit early for some of the other dating that goes on in some of the other historical records at the time. But this middle one listed here, that happened in 5 BC, March, April of 5 BC, is intriguing. It is thought to be what the Chinese called a broom star, meaning it had a tail. The other 2 stars listed here were the fuzzy sort of tailless comets. And this is an interesting one. Again, I still don't read Chinese, but I'm told this is the catalogue entry of a particular comet that was seen by the Chinese in March, April 5 BC, and may correspond to the one seen by the Magi. If it did, it lasted a surprisingly long time. 70 days is a very long duration for visibility of a comet from Earth. Is there anything else? Are there any other details that can fit together to give us a sense of whether this might be a plausible identification or not? Can it be refuted? Is equally an important question. Well, I mentioned that King Herod had a bit of a tantrum when the Magi rocked up on camelback and said, "We reckon we've seen something in the sky, which means to us there was a newborn king somewhere." Herod threw a tantrum. He was apparently notoriously insecure. And apparently, when the Magi went off to head down to Bethlehem, Herod, meanwhile, before the Magi disappeared and headed off, Herod apparently quizzed them on exactly what did you see? Exactly when did you see it? What have you seen? It's plausible, though by no means certain, they might, as excited astronomers, have mentioned the triple conjunction that they saw 2 years previously in 7 BC. They might have also talked in 5 BC of the comet. Of course, we can't know, but what does seem to be part of history is that Herod decreed that toddlers, or boy toddlers, who were under the age of 3 should be massacred. And there have been a great many representations of the massacre of the innocents throughout art in history. I'm showing one here. Why would anyone want to kill anyone else? Why would anyone want to massacre toddlers? Why would he specify that they were little boys under the age of 3? Maybe he didn't want to take any chances. Maybe, having heard that there were fireworks in the night sky with this these 3 successive great conjunctions in 7 BC, he wanted to obliterate any little boy, boys only because only boys become kings, any little boy who could have been born since any celestial spectacle was seen in the night sky that the Magi were talking about. Is 5 BC a problem? So far as I'm aware, it's not. And I think for any concordance of this historical narrative, it seems fairly certain that these events with the Magi would have to have preceded Herod's death, which was apparently in 4 BC. So it is possible that by piecing together these different accounts, sparse though they are in detail, but bringing together the Chinese records and the scant details in Matthew's Gospel from analysing the New Testament Greek, perhaps it is possible that, as Colin Humphreys lays out in his paper in the Quarterly Journal of the Royal Astronomical Society, perhaps one can attain some chronological uncertainty and date the birth of Christ to April in 5 BC. It is possible a few other details then fall into place, such as that would have put it at Passover, which would be a reason why there was no room at the inn, and hence the whole stable and manger thing happened. It might explain that detail about shepherds on the hillsides watching their flocks, because after all, April is lambing season. Well, the Chinese records may give us some sense that that was the particular comet. What we don't have yet is corroborating observations that would enable an orbital solution to give greater clarity, or perhaps more of a strong clinching argument to that particular identification as the Star of Bethlehem. The comet would have been seen for longer still and by more people if it had been closer to Earth. But it's jolly dangerous if comets and asteroids get too close to Earth. For example, in 1908, the morning of the 30th of June 1908, over Siberia, there was a bluish light said to be as bright as our sun. Fireworks in the night sky are all very well, but in the morning when you're eating cornflakes, possibly not so much. Apparently there was an airburst, then a shockwave of an explosion thought to be from a stony meteorite. The impact event actually occurred not on the surface of the Earth, but 5 or 10 meters in altitude above the surface of the Earth. Forests for miles around were flattened by the force of this airburst, this explosion. It was reported to be something like magnitude 5 on the Richter scale. So if asteroid explosions or comets get too close, yes, in principle we can see them for longer, but too close, that's pretty bad, I reckon. We do know of other impact events that actually impacted the surface of the Earth, the most famous of which perhaps is the Beringa crater in Arizona near Flagstaff. This is over 1 meter in diameter. Modelling suggests that it was formed over 50,000 years ago by the impact of a nickel-iron meteorite, some 50 meters across, travelling at something like 12 meters per second. It is also thought that the impact of a big meteor on Earth causing a massive climate change is what is responsible for wiping out the dinosaurs. We don't have any artistic representations of that time, of course, hence this speculation here. Well, I would like to close by wishing you a very happy Christmas in whatever way we may celebrate this 25th of December. It is fascinating to ponder that what we may be celebrating, the original event, may not have been in December, may have been in April. It is fascinating to ponder that it may have been witnessed by celestial fireworks. It is true, we live on a dangerous planet, but please keep looking up. Thank you.